All right. Hi, everyone. I'll be presenting this quick and fun talk about zk benchmarking. Hopefully, it'll be very useful to all of you in your next projects. This one is not so much about theory, so sit back, relax. This one is going to be like a fun one for all of you, right? And yeah, I think Zach also teased out this part a little bit during his early session, right, wherein he said most of the benchmarking today is all juice and all fugazi, right? People just throw a bunch of numbers, and those numbers, always people take that with a grain of salt in zk benchmarking. And so far, the benchmarking has in the zk landscape has been very poor, but things have started to change. This paper actually came out last week in preprint, so it's very, very cutting edge and very useful to all of you, I'm sure, right? So let's get on with it. It's a short one, right? So it's called zkBench, right? Yeah, so I'll probably set the agenda of what I want to cover, right? So by zk benchmarking, right, we want to know a few things, right? We want to know how much. So let's say you have one circuit, you're a circuit developer, and you have like 20 proof systems in front of you, and you want to decide which one should I pick, right? Should I go with the Halo 2 or should I use Sarcom, right? Which one should I pick? And there is this other use case as well, wherein you're like a protocol designer, right? And you want to test with a bunch of libraries. Should I use this this arithmetic library? Should I use the ArcWorks implementation to build my algebra and arithmetics in my proving system, or should I use this GNARC library, zk crypto, right? There are a bunch of these arithmetic libraries. So there are a bunch of use cases for benchmarking in zk, right? Yeah, so we would define certain measuring standards on which we can measure our benchmarking numbers, and then I'll show you how this benchmarking framework actually works on a very, very high level. And then we will actually look at some results on some of the most popular proving systems and frameworks available today. We'll compare how all of those work, right? And we'll conclude by what's missing in this framework and what can be added in the coming months, right? Right, and what this talk is not about, so there is this flaming war going on these days on Twitter about is Stark better, is SNARK better, which is going to win, right? So we are not going to touch on any of those touchy topics. And also some of the results that I'll be showing later, right, are not timeless. So these might keep changing, right, because it's heavily dependent on the optimizations and the way these circuits are written. So these numbers might keep changing, so take it with a grain of salt again, but should give you a good intuition. And yeah, so I think everybody knows what SNARK is, so I don't think I'll be covering this, but maybe it's worth highlighting the setup phase. I think everybody knows what proving and verification is, right? But most of the SNARKs available today, right, have something called as a pre-processing setup, and it's a two-step setup. It's a split setup, right? So it has two phases. One is the randomized phase at the beginning, wherein you generate the toxic waste, right? And then you use that toxic waste and feed that to this algorithm called as indexer, along with the circuit parameters to generate the proving and the verification key, right? So this on a high level is how a SNARK works, right? And again, this block diagram kind of summarizes the basic steps in all the modern SNARKs. So it has, we like to categorize that into two stages, right? The front end and the back end of a proving system. So the front end consists of the circuit actually, and how you generate the intermediate representation of the circuit. So you feed the circuit file and it outputs you R1CS or a AIR representation, right? So all that is included in the front end part of it. And then we have the other more interesting part, which is the back end part, and which is what we'll be focusing more on. So this consists of the setup phase, which I just described, right? Wherein you feed in the parameters, and it outputs you the public and the public key and the verifier, the prover key and the verifier key. And yeah, the backend also includes the proving engine and the verification part, right? And this is primarily what the benchmark delves into. We are more focused on the proving numbers, the verification, how long the setup takes, right? All of this. Right, I kind of described this. So if you're developing a new SNARK, right, you kind of have two use cases. One is if you're actually a protocol developer, right, if you're developing something on the Halo 2 framework, let's say, and you want to decide which is the best underlying arithmetic library that I should go with. So there are ZK developers doing a lot of this, and then there are application developers who are just planning to use some existing DSL and just trying to know which one is going to be the most optimal for my use case, right? So for both of those use cases, we kind of want a benchmarking framework or a library which satisfies a lot of these requirements. So on the framework side, right, we want a framework which is holistic, which covers, which gives you data about the underlying finite field operations, the elliptic curve operations, the end-to-end circuit operations, right? You want that framework to be modular. By modular, I mean every time you write a, every time, let's say you have supported Halo 2 on this benchmarking framework, right? And every time you want to support a new circuit using Halo 2, it should be very easy for a circuit developer. You don't have to keep reinventing the wheel all the time, right? And again, it should be reproducible, pragmatic, yeah. So this is what we kind of want in the framework, and these are the things that we will be measuring the framework on. So we want to measure how long does a whole ZK proof generation take, right? The whole execution end-to-end time. How much memory is being consumed while generating these proofs? Again, important criteria. How long is the proof size at the end, right? Something like a SNARK generates a proof which is maybe hundreds of times larger than a SNARK proof, right? So we kind of want to benchmark those numbers, right, along these metrics. All right. So this is like the important part. So this is the architecture of the benchmarking framework that has been proposed, right? So so we have two parts to this. The first block is where we are trying to actually benchmark the underlying arithmetic library, the library which is doing these arithmetic operations on the finite fields, right? Or the like additions and scalar multiplications, pairings, all of that. We want to benchmark those libraries. So for example, ArcWorks, GNARC crypto, right? So this is one part of it. The second part is actually benchmarking the circuit, right? So let's say you have a SHA-256 ZK circuit, and you want to benchmark that same circuit across various proving systems. So something like Bellman or GNARC, right? So these are the two parts to the framework, and you run the benchmarking framework, you generate standardized logs, and that logs gets parsed by the system, and you get beautiful visualizations at the end on the UI, right? And this is something that you can go in your browser and try using today. So one is called as zcalc and the other one is zk harness, wherein you can test out, you can put in a circuit and it will spit out information which one is actually more useful to you. All right, so in this paper they tried running a whole bunch of benchmarks on a lot of these popular curves and a lot of popular crypto libraries that are used in a bunch of ZK frameworks. So something like the pasta curves, the ArcWorks library, the Halo 2 curves, right? All of these are like commonly used, and they try to run these on, in the paper they say they run this on 13 different type of curves. So it can be BLS family, the BN family, the pasta curves, right? This is what is currently supported in the benchmarking framework, and then we also run some benchmarking tests on 5 popular proving libraries, and that includes the Bellman, the Halo 2, GNARK, SRCOM, and the STARKey framework, right? And yeah. And in the paper, they run 2 different type of tests, and one test is just modular exponentiation, a simple circuit wherein you just keep exponentiating it for 2 to the power 24 times. So that gives you about 9 million constraints in the circuit. And then you also run a SHA-256 benchmark on all of these proving systems. And we run these tests on 6 different type of machines, starting all on AWS, starting with a very tiny machine of little memory. And then we also run it on the ARM and the x86 architecture. And we also at the end run 2 tests on a CPU optimized machine and a RAM optimized machine. Okay. All right. So coming to some benchmarking numbers now. So these are some numbers for the MSM operations across a lot of these underlying arithmetic libraries, right? So if I have to give you like the TLDR summary, right, of all of these graphs, what we see here is the GNARK library is probably the fastest right now, and the ones implemented in Wasm and Rust are performing quite slow. So something like FF JavaScript, right, is one of the slowest ones, right? And these are some numbers for the SHA-256 tests. But again, these circuits are heavily dependent on the actual implementation of it. A lot is dependent on the optimization. So some libraries have done really good work here. So something like GNARK, right, have implemented the SHA-256 really well. So they have really good numbers right now. And yeah, that's the reason why you see GNARK taking very little time, and something like SNARKs taking like 20 times more for the same circuit. Right. And this is again one more interesting test that was done. So you take the same circuit and run it on just 2 different type of machines. One machine has higher memory and the other one has higher CPU. And you see some surprising results, right? Some libraries perform well in CPU optimized machines, and other proving libraries perform well on memory optimized machines. So something like a rapid SNARK, right, performs really well on a machine having a lot of memory, right? But something like GNARK is performing really well and on CPU optimized machines, so it does not really care so much about the memory. So these are like interesting statistics that you'd probably want to be interested, right? Every time you develop a circuit, you should probably see if I would need a machine that is more which gives me more memory or which has more CPU, right? So again, I found this quite interesting, this test. Right? And yeah, this is again one big goal of this library, and this I think is going to be very useful going ahead. So so far, in my opinion, we have not been able to estimate how long will the proof generation take, right, accurately. So we have a circuit with us, and we want to know if I run this on this particular machine, how long would the whole proof generation process take, right? But now with this benchmarking numbers, we can actually get like a good understanding of how long we can estimate how long the whole end-to-end process will take based on just the numbers of the underlying libraries being used, right? So this paper ran a whole bunch of simulations, and they gave error rate less than 25%. So you can kind of create a custom circuit, and you can have like a good intuition with about 25% error rate of how much the whole process will take. Yeah.
Based on what? Like what do they count?
So they take the MSM, the FFT operations into account.
Okay.
Like the underlying the finite field libraries, the algebraic libraries, right? Based on those numbers, they kind of build the number.
So, for example, like how many MSMs will this circuit take?
Yes,
And then based
yes,
on what library
right, right. But again, this is very, very implementation dependent again. So, for example, right, Groth 16 verification has 3 pairing checks in it, and some libraries try to optimize that verification and just use. So, if you have 3 pairing checks, right, that would involve 3 Miller loops and 3 exponentiations. But some libraries do just 3 Miller loops and 1 exponentiation. So, there are these subtleties that are happening across different libraries. So, that is something that is difficult to capture, hence the massive error rate sometimes. Okay. So, this is what has been done so far in this benchmarking framework, and this is something that the authors say is in the pipeline for the coming future, right? So, right now they do not incorporate recursion techniques, folding schemes, right? So, we do not really have benchmarking for doing that. And again, these estimations are not up to the mark. You want to estimate it for more complex circuits, and if you have lookups and foldings, right, you kind of want to incorporate those runtime estimations too, which is not happening right now. Yeah, I think, yeah, that is it. You can try. Yeah. You can maybe have a look. There is this website called as zka.lc, wherein you can actually run a whole bunch of benchmarking tests on the arithmetic libraries. Very, very good website, zka.lc. And there is another website called as zk-bench. If you Google that, you'll find. So these two are using this framework and will be quite useful going ahead. Yeah, I think that is it. If anybody